Hello and welcome. My name is Matty, and this is the next episode of Vocation. Once again, I'm very pleased to announce I'm joined by the great Ralph Ellis. And today we're going to be speaking about your Ice Age paper, your paper on climate science, Ralph. Can you give us a little bit of an introduction? We spoke about this last week, but can you maybe set us up once more? I think we were meant to get into the details, but we did a macro
Yes,
review.
last time was interesting. We did a 2-hour introduction,
Yeah,
so
just
I'll
a
make
quick
this
one.
one a little bit shorter.
No worries.
Yes, so this is my Ice Age paper. I was talking to these people online, including senior scientists, and it transpired that nobody knew how ice ages were modulated, you might say, how they were influenced by terrestrial feedbacks. So it was a mystery, and it was a mystery that needed solving. So I thought, well, I'll have a go at this. And the main thing you touched on last time is the thing about CO2. Of course, in the modern world, everything has to be CO2. So they say the feedback agent that helps give us interglacial warming is CO2. It has to be. CO2 is the miracle molecule. It does everything. But we had that conundrum we saw last time where when CO2 is high, the world cools into an ice age. And when CO2 is low, the world warms into an interglacial. Not what you might expect if CO2 was the primary feedback assisting with interglacial warming. The second thing I noted, which not really I think many people have noted in their papers, because I think I read 70 papers when making my paper, because you've got to reference everything in your paper to previous scholars, previous papers that have, been written and approved. So you've got to read all of the literature. And not many people point out that interglacials are northern hemisphere events.
Hmm.
Now, and we'll see why in a minute when I bring up some graphs. But you would have thought with CO2 being a global gas, you would have interglacials on southern hemisphere warming or
Mhm.
northern hemisphere warming. But we don't. It's only ever on northern hemisphere warming. So that's a conundrum.
Interesting.
And there were a
Mhm.
few other sort of basic conundrums like that. And they sort of had me thinking a little bit. And I decided to find out why we have interglacials. Because we're in an ice age, we've been in an ice age for a couple of million years now with various little warm bits, and we happen to be in a warm bit at present, an interglacial. So I'm just going to do a screen share. So do jump in if there's something you don't understand, because I might gloss over things because I've been through this
Mhm.
so many times. I know this subject very well, and it's very easy to confuse people.
Yeah, fair enough.
So let's try and get that as big as I
Um,
can on the screen.
yeah, dead on.
Excellent.
Even just maybe set it up a little bit more. How often does an ice age last? How many have we had? And how long have we not been? How long have we been in this warm interglacial period? Maybe.
Yes, good question. We'll see a graph on that in a minute, but we've been in the ice age of large ice ages, like the present one, for about 800,000 years. And each ice age lasts about 100,000 years. And each interglacial, most of the interglacials are only about 5,000 years, so very short. So you get a lot of ice for a long time, little tiny interglacial, and then straight back into freezing conditions again, except for when there's low eccentricity, and we'll look at that in a minute. And then we get longer interglacials, and the eccentricity cycle, it's a cycle of the Earth going around the sun, obviously, is 400,000 year cycle. So 400,000 years ago, we had a long interglacial. And this time again, we've got a long interglacial. So we've been in this interglacial for more than 10,000 years. It started about 17,000 years ago, just gently, and then it shot up about, I don't know, we'll have a look on the graph in a minute, about 13,000 years ago. And we've been in the interglacial warm period ever since, except for the Younger Dryas, and we'll look at that as well. So that's the basic. And before 800,000 years ago, or before 1 million years ago, we had little ice ages, not the big ones that we have now. So they were regular every 40,000 years, and quite obviously driven by the obliquity cycle. These are the same cycles we've been using when we were dating the pyramids and so on. It's the same cycles: the precessional cycle, the obliquity cycle, and now we add in precession as well. Sorry, and not precession, eccentricity, that comes into it as well. So, and what generally they say is that you get these orbital forcings where it changes the amount of insolation, the amount of sunlight hitting the Earth in the northern hemisphere. But that's not enough. You need a feedback agent that helps the orbital cycles. So the orbital cycle is known as the Milankovitch cycle, after Milankovitch, who was a Serbian scientist who discovered this cycle about 100 years ago or so. And they had to do all the calculations manually, so they did it fairly roughly in modern terms, because it was all done manually. And he had a team of about, 30 women all doing these calculations, because they're fairly complex, to see the effects of the orbital cycles on the Earth. Nowadays, of course, you put it into a computer, you got the answer in 30 seconds. How things have changed. But this picture here is the CO2 effects. And this is important because CO2 is a greenhouse gas. It's not as powerful as they say. So in my view, I agree with people like Dr. John Christie, who's the senior climate scientist for Alabama. And he says that the effect is only 1.1 degrees centigrade for a doubling of CO2, which is about a third of what the IPCC will generally say. So there is evidence that CO2 is not as powerful as the IPCC keeps saying. And if you note, if you've been watching the news recently, they've just scrapped RCP 8.5. RCP 8.5 was the worst scenario in the IPCC warming. They've got these various different scenarios. And that was the one they always trotted out to say, we're going to fry, we've got global boiling. That was always RCP 8.5, which was the worst scenario. Yeah, sorry.
Just to step back for a wee second again, the IPCC, this is the Intergovernmental Policy for Climate Change, is that right?
Yes,
yeah, something like that.
And
this is a UK-based body with it, or is that international?
No, it's international, yeah. It was originally, it was run by an Indian guy. It was run by Pachkuri, I think his name was, who was an Indian railway engineer who ran the IPCC, and he wrote smutty novels.
Right. You've really dug into this, Ralph.
Yes. So if you're at an IPCC meeting and you ever see a silk handkerchief on the floor, don't touch it. Yeah. He was a curious character writing these, smutty novels.
And so this was the gentleman, this is the governmental body that was coming up with the different climate models. They put different assumptions into these, then they run them into computers. But obviously they go with the worst case scenario possible and then make all government legislation based on that. And that's what's
RCP 8.5 was suggesting that we would burn more fossil fuels than there are in the Earth. I mean, it was just absurd. They were going up to, by year 2100, they were going up to 1,200 parts per million CO2. We're currently at 400. And it's almost impossible to get to that amount of CO2. There isn't enough fossil fuels in the Earth.
What other major predictions did they have in this modeling then that you can recall? How much the temperature was going to rise, or maybe these sorts
Well,
of things?
RCP 8.5 was going to put up the temperature by about 7 degrees.
Jesus, by 2100, is that correct?
Yeah, by 2100. Now, these temperatures, normally they're quoting Arctic temperatures, not necessarily, because due to polar amplification, they call it, the temperature change is much greater in the poles than it is in the tropics. So that's worth noting, actually, before we start. When we say an ice age, that's the temperature in the poles got really, really cold. And by
Hmm.
really, really, I mean 12 degrees colder than we have now. So that's about the
Wow.
range. But in the
Yeah.
tropics, the temperatures only change by a couple of degrees. So in the tropics, you wouldn't really have noticed that there was an ice age. Life would truck on as per normal.
That's
Um,
interesting.
yeah, so it's really it's a polar effect of, and of course that means the ice comes further and further south because the poles are very, very cold. And RCP 8.5 was saying 7 degrees of warming in the polar regions. And all these terrible predictions about what would happen. But remember, during the Holocene maximum, and we'll look at this in a minute, which is only 8,000 years ago, temperatures were up to 5 degrees warmer than now anyway, and just
Yeah.
naturally. Um,
Yeah.
so the poles were much warmer 8,000 years ago. And at the same time, the Sahara Desert turned into a tropical paradise. So the
8,000 years ago.
Sahara Desert
Yeah.
was covered in rivers and trees and hippopotami
Hmm.
and all sorts of things. So
Hmm.
yeah, climate changes. This is why it's such a stupid thing to label it as climate change. Climate
Yeah. Yeah.
changes all the time, with or without mankind's inputs. So a lot of this is just scaremongering, basically. When they say, the world will end in 7 years because temperatures are going to increase by 3 degrees. Well, temperatures were 5 degrees warmer 8,000 years ago, and the world was fine.
Uh, no one brings this up, Ralph. This is the first time I'm hearing this. Yeah,
Right.
yeah, yeah. It's unreal, isn't it? Because it just falls in his face, some of these
Yeah,
arguments,
we'll see this in a
Yeah,
minute. We'll see the evidence. And, not only was the world fine, but it was better than it is now. Warm is good, cold is bad, cold kills. Um, you know, uh, Warm generally is much better, especially as during the warm periods, again, the tropics don't change very much. So you wouldn't notice the difference in the tropics. What it means is you get a great expansion of the available land that is available for plants and animals, the whole biosphere. And the other thing that happens as well is CO2, since we've got this CO2 picture up here. CO2 is not only a greenhouse gas, it is plant food. So CO2 is the most important gas in the atmosphere, which is why it was so stupid when the EPA in America, the Environmental Protection Agency, declared that CO2 was a poison. No, it's the most essential gas in the atmosphere. Without CO2, all life on Earth will die. And that's what we see here. So on this graph here, we've got plants growing. Now we're looking at the top, which is C3 plants. The bottom is C4 plants, which is things like maize and sweet sugarcane, things of that nature. Fleshy sort of plants. Now they can withstand much less CO2. It's a very recent modification in plant life, an evolution due to there being not very much CO2 around. And so we have this new type of plant has come along, which is known as C4. But most of the plants are C3, which is the top one. Oh, I've got I've got my little index pointer on the wrong thing. Here we go. So I'll point at the right thing now. Yeah,
yeah.
C4 is the bottom graph,
Yes.
and
Yeah.
C3 is the top. Along the bottom is concentrations of CO2.
Mhm.
So we're at present at 400 CO2 here, parts per million.
Mhm.
When you get down to 150 parts per million, all C3 plants will die.
Right.
Now, they're not dead here, but what happens is they cannot complete a life cycle. So
Mm.
they can't reproduce. And so C3 plants will die at 160 odd parts per million. But the more CO2 you get, the better plants will grow because it's
Mhm.
plant food. That's why if you go to Holland, where they have acres and acres, miles and miles of greenhouses, the greenhouses, they pump up the CO2 to 1,500 parts per million.
1,500. Wow. Yeah.
1,500, yeah, absolutely.
Mm.
And that's okay for people to walk around it. If you go into a lecture hall with lots of people,
Mhm.
CO2 will be at 2,000 parts per million.
Right. Yes.
And so you get
Yeah.
all these people saying, oh, it's a poison, you'll die, you'll die. Lecture halls run at about 2,000 parts per million because there's so many people in there
Mhm.
breathing out CO2. Your breath is 40,000 parts per million,
I
4%
see. Yeah. Yeah.
CO2.
Right. Yeah.
And so, if you're kissing someone, you're breathing 40,000 parts per million. People don't often die from kissing.
Not often.
They probably catch other things from kissing, but they don't die from it.
Yeah.
Um,
Yeah.
So yes, CO2 is the most important gas in the atmosphere. And you'll notice we've gone from 300 to 400, how the plants have increased. Agricultural production has increased by 20% because of extra CO2.
Over what time frame there? The last 150
The
years,
last
industrial era,
30
is it?
years. Last 30 years.
Last 30 years, we went from
Yeah.
300 to 400. Right.
Yeah.
Right. Yeah.
So we are now feeding the vast population we have on Earth with extra CO2. If we didn't have that CO2, we would probably have starvation going on because agricultural production has increased by about 20% due to CO2. No, it's increased because of better agriculture. We have better fertilizers, better machines for tilling the soil, everything, but also they're growing better because we've got extra CO2 in the atmosphere. So CO2 is actually a big benefit to the biosphere and to mankind. NASA did a study on this recently. It was about 4 years ago, called The Greening of the Planet, I think it was called. And they can actually see that the world is greening from their satellite observations due to extra CO2. So yeah, CO2 is good for the planet. This is CO2 over millions of years. So this is going back a long way. This is zero on the right here, going back millions of years before present. So here is 500 million years before present. And we have the, this sort of bluish line is temperature, and the purple line is CO2. And there's not very much correlation between the two. They're saying that CO2 is the only agent almost. Well, it's not true because water vapor is the biggest greenhouse gas. CO2 is secondary. But everything is caused by, all the warming is caused by CO2. Well, there's not a great correlation here. Where temperatures dropped here at the end of the Jurassic, CO2 was going up while temperatures were falling.
Mhm.
And I think we've got, where have we got? Well, you can see there's a great lack of temperature here, but then temperature rose while CO2 was low during the Triassic.
Just a quick wee question. The sharp drop-offs there, is that to do with cataclysms occurring more so, or is
No,
this the cycle we're speaking of?
it's plants. Plants will kill themselves. I mean, there is no control over what's happening on the Earth. It's just what happens, basically. And plants will draw in CO2, and animals will draw in CO2 as well, especially sea animals. And they will die, and they will go to the bottom of the sea, and they will create limestone. That's locking away CO2. Plants will die. They will go to the bottom of the sea, or they will go into marshlands or whatever, and they will cause fossil fuels, coal and oil and gas and so on. That is locking away CO2. So all the time here, you see all the way back from the Cambrian, okay, that's a long time ago, 500 million years. Plants and animals were locking away CO2, locking it away all the way down here. And so there was getting less and less CO2. And so the world was strangling itself because it was consuming its own feedstock, its CO2, which is the most important gas in the atmosphere. And so the world could have died completely. Well, I mean, the biosphere could have died. And the only thing that saved us from complete extinction was mushrooms.
Right. Those magic
So the
things.
world,
Yeah.
yeah, hooray for mushrooms.
Yeah.
So mushrooms came along, and they found a way of feeding on lignin in trees. And so now, when this is, about the Triassic sort of era here, now when trees died, fungi could actually attack it and break it down, the lignin, and so release that CO2 back into the atmosphere, which is why the Carboniferous age ended. So here's the Carboniferous age here. They've got it 360 million years ago down to 290 million years ago. That's when all of the coal seams and the oil was being locked away in the ground. And after that, fungi started releasing CO2 back in the atmosphere.
Mm-hmm.
And that saved the biosphere. Otherwise, everything would have died. And so then we got more.
Just a quick question just on that era as well. I can see the temperature sharply rose again before the release of the CO2. What's your understanding of why that sharply increased once again?
Well, there is no, I don't think, I've not seen an explanation for that, but there is not a good correlation between CO2 and temperature. I mean, CO2 is a greenhouse gas, but it's not the primary. We'll have a look at this in a minute. It's not the primary feedback agent. Now, when this temperature went down here, this was going down, and this one here as well. This was going down to what they called the snowball Earth. So the ice age got so big that it was going to encompass the entire globe all the way down to the tropics. And if that had happened, then everything would have died. There would have been no life on Earth, of course. So it was lucky that CO2 was released back in. Now, originally they were saying that this was volcanic activity all of a sudden. I don't know why. But of course, a lot of that CO2 was being released by fungi as well. And that's why we got a rebound in the amount of CO2. And the temperatures went up. Now, one of the reasons why the temperatures went up might have been ice sheet feedbacks, which is what my paper is about. So we'll have a look at that as well. So if we get dirt onto the ice sheets, they absorb more sunlight. And so the temperatures went up, and now they've been decreasing. This is from 65 million years ago. Temperatures have been decreasing all the way through the tertiary and quaternary periods. We've had a steady decline in temperature, and we've had a steady decline in CO2 as well, because remember, animals are still locking away CO2. Every time a sea animal dies and its bones go down or its shells go down onto the seabed and forms limestone, that's locking away CO2. It's all being shut away. And again, we got down to CO2 levels where all life on Earth could have been extinguished. And the only reason CO2 has gone up is because we have released some CO2 by burning fossil fuel. So
Burn
the
more.
big oil is
Yeah.
the savior of the biosphere. Without big oil burning and big coal and big gas burning fossil fuels, all life on Earth might have ended.
Well,
Not
it's
within the
quite the
next
headline.
1,000 years, but within
Yeah.
the next 50,000 years, next million years, sort of thing. If we'd continued locking away CO2, we'll see how close we came to at the last ice age. We nearly wiped out C3 plants 20,000 years ago. I mean, that's how close we came to wiping out a lot of the life on Earth.
It's extraordinary.
Yeah, so big oil has saved the biosphere. It's allowed plants to grow again, which they weren't before. So that's millions of years ago. Let's have a look at thousands of years ago. So this is same idea. This is so temperature is the top one here in black. That's temperature. This is from, let's look on the right-hand side. 0 on the right is today's date, back 11,000 years. So this is the Holocene. This is our interglacial period. Like I said before, the interglacial is extended this time. And we've been at least 12,000 years in the recent ice age. And we've got a few thousand years still to go. So this is temperature. They've drawn a purple line against it because you can see the temperatures went up. Temperatures were much higher 9,000 years ago than they are now. Than they are now. So it was much hotter during the Holocene maximum. They've drawn this purple line in because some people think that this decline in temperatures is due to the decline in obliquity, the Earth's leaning angle. And so the purple line is obliquity. They've drawn that in because they think that that is reducing our temperature at present, reducing obliquity, the leaning angle of the Earth. CO2 is in red, and again, you'll see there's no correlation between warming and CO2 whatsoever.
Yeah.
So
Jeez, it puts it to bed, doesn't it? These last two graphs that's just the nail in the coffin, really, isn't it? When you zoom out,
yeah,
you get the macro picture.
as temperatures are reducing, CO2 has increased because it's a complex interaction between what CO2 is doing to the oceans and what CO2 is doing to the atmosphere. Now, this is complex. I did go into this at some point, and I've forgotten exactly what they said, but it's to do with the declining, because here, when it was warming, plants were growing because warming is good for plants. So more and more plants were growing, which drew down the CO2.
Yes. Yeah.
So as temperatures increased, CO2 reduced because the plants were locking away CO2. This changed the alkalinity of the oceans. Forget this acidic oceans business. Oceans can never be acidic. Again, that's a scare story that they like to tell. Oceans are alkalinic. But there was a reduction in the alkalinity of the oceans, and this allowed more CO2 to come out of the oceans despite cooling, because normally when you get cooling, CO2 is locked away in the oceans. But we had the reverse here, and they were explaining this to do with the pH of the oceans. Now, I don't know if that's correct or not, but that was the explanation, because it is totally the opposite of what you would expect as CO2 as being a primary warming feedback. So as CO2 rose, temperatures fell. And this is over 7,000 years. No correlation between CO2 and temperature whatsoever. and then we get our little bit at the final end here. We get an increase in CO2 and supposedly an increase in temperature. But remember, there's been many spikes in temperature during this time. We had this is, I think, here, the Minoan warming. Then we had the Roman warm period. We had the medieval warm period. So there are many spikes in these temperatures, and we'll see more in a minute because it's worse than this. No, we'll see it in the next lecture, which is about Carolina bays. I think I've put that in there. So anyway, yes, 8,000 years ago, well, here they've got it between 10,000 and 6,000 years ago, temperatures were warmer than they are now. Now, again, these are Arctic temperatures, not tropical temperatures. All of these temperature changes really take place in the northern latitudes.
Mm-hmm.
And we know it was warmer. These are taken from proxy temperatures. They take this from ice cores. They take it from stalactite cores and so on, giving you proxy temperatures so you know the temperature in the past. And the temperatures they give are relatively trusted and accurate. But another way we can prove this happens, because obviously we're just using proxies. We don't have temperature gauges, 8,000 years ago. We're only relying on these proxy changes in the ice cores. But we know it was warmer because of tree lines. And so this is two maps of two different types of tree. So this is the Arctic shoreline. This is up in, northern Russia. And this is Betula, which is a type of conifer, obviously. Now, the current limit of Betula is this dotted line here. That's how far north it will grow. And it can't go any further north because it's too darn cold. But 8,000 years ago, it went all the way up here. Now, that is, 3 degrees of latitude. 3 degrees of latitude is 180 nautical miles. Call that 350 kilometers. So the tree line was further north by 350 kilometers because it was warmer 8,000 years ago. And so we know, we have proven that it was warmer during the Holocene maximum. And this is the same with a different type of tree. This is the larix tree, and the extent further north is less with the larix than it is with the betula. But there we go. It's a different type of tree. So we know that the Holocene maximum was actually much warmer than now because these tree lines have still not recovered. So the trees have not extended as far as they were 8,000 years ago. This is temperatures for the Holocene. This is a different type of no, I think that's using the same proxy. This is using change in oxygen 18, an isotope of oxygen. And again, we've got today's date on the right, going back 20,000 years. This is a graph of temperature. And no, this is just change in oxygen 18. This is not actually temperatures. This is change in oxygen 18. Anyway, it was cold. This is like 17,000 years ago, 15,000 years ago, and 15,000 years ago, the interglacial started. And we get this sudden increase in temperature. And it rocketed it up, and then it stalled, and it rocketed back down again. And that is known as the Younger Dryas. The Dryas is a type of plant that they find, and it's indicative of cold temperatures. And so we went back into an ice age for 1,000 years. And there's lots of speculation as to why that happened. I am still in favor of this being a meteorite impact that sent us back into a temporary ice age of 1,000 years. And we'll look at why that is in the next talk, because this is connected with the formation of the Carolina Bays. The Bay Mystery, another big mystery that is not explained, but we'll look at it.
I see. Yeah.
And then the Younger Dryas, it finally fizzled out after 1,000 years, and suddenly we got this warming again, and we were back into the Holocene, up to the Holocene maximum, about 9,000 years ago when it was warmest, and we've been cooling ever since. And this is us now. So, all of these mysteries prompted me to try and find out why we have these interglacials, because the CO2, as we've seen, is not a good explanation for why we get interglacial warming. So I wrote this paper. So this is my paper together with Michael Palmer. Michael Palmer is a chemist, but he's written many papers, whereas I have not written a paper previously. And so I got a lot of coaching from Michael on how to write a paper, because there's a specific way you have to write them. And he was handy dandy with all of the graphs we had to make as well. So between us, we wrote this paper, which is modulation of ice ages via precession and dust albedo feedbacks. Sounds complicated, but it's not. It's just how much dust you get on ice sheets, because dusty ice sheets are darker ice absorbs more energy. Now, other people have attacked this and put it into papers, but always as a secondary effect to CO2. And they've misidentified how we get dust in the first place. And so my paper sorts out both of those and explains everything. So this is a paper which has been out. When was this written? This was written in 2016, so 10 years ago. It's not been undermined yet. It's not been challenged. It's had 45,000 downloads, so it's well known. That's very high for a paper. Papers often only get a couple of hundred downloads, If that sometimes, yes. So it's done very well.
Fantastic. We'll leave a link down below.
Yes, you can. Yes, yeah. I'll give you the link, and you can put the link down below as well, so
no
people
worries.
can click on it. It's not best liked in the industry, of course, in academia, because it goes against everything that's been taught. It's saying that CO2 is only a minor player in the ice age cycle. But nevertheless, they've not been able to falsify it, and so it stands as it is, as a very viable explanation for why we get ice ages.
Should we read the abstract, Alf, or are you happy just to jump in?
Well, we can start on the abstract a little bit, yes.
It might be a good framing.
It says, we present here a simple and novel proposal for the modulation and rhythm of ice ages and interglacials during the late Pleistocene. While the standard Milankovitch precession theory fails to explain the long intervals between interglacials, we'll see why that is in a minute, these can be accounted for by a novel forcing and feedback system involving CO2, dust, and albedo, but involving CO2 in the reverse sense, which is why this is a controversial paper. I'm saying low CO2 causes warming, just to upset them, During the glacial period, the high albedo of the northern ice sheets drives down global temperatures because it's bright white, and drives down CO2 concentrations because the seas absorb more CO2 when it's cold. Despite subsequent precessional forcing maxima, despite the subsequent precessional forcing maxima. We'll look at that as well. Although the orbital cycles change, the temperature doesn't. Over the following millennia, more CO2 is sequestered in the oceans, and atmospheric concentrations eventually reach a critical minima of about 200 parts per million, which, combined with arid conditions, causes a dieback of temperate and boreal forests and grasslands, because CO2 is plant food. It's the most essential gas in the atmosphere. So without CO2, the boreal forests, that's the northern forests and grasslands, especially at high altitude, begin to die off. The ensuing soil erosion generates dust storms, resulting in increased dust deposition and lower albedo on the northern ice sheets. And that's the essential thing. So what has not been done in most of these, the vast majority of these papers on ice age cycles, is they've not included dust. There are one or two. There's Ganopolsky and there's Marwold. But Ganopolsky said it was ice sheets pushing across the land and causing glaciogenic debris and dust. I think he was thinking about the Disney Ice Age scenario, I think, where we have those cartoon characters and you get this big ice sheet as a wall of ice going across the land. I mean, that's not how ice sheets work. So, and the dust is not glaciogenic because the dust comes from China. It's Chinese dust.
Right.
It's from the Taklaman. Takalaman? Anyway, the desert over there. And the Gobi is where the dust comes from.
So just to make sure, everyone's following along very simply. Mainstream narrative is that high CO2, this means higher temperatures, ice ages ending, polar ice caps melting, we're all going to die. This is sort of the main thing. What you're saying here is lower CO2 means there's less plant life. This means the soil erodes more because you have less trees and things keeping it all together. That extra dust that's generated from this poorer soil combines with the ice on the ice caps. That leads to them absorbing more light. That's them heating up. They're melting in that way. And this is how we get a warming, is from a lower CO2 because there's less plant life. So just to make sure
so it's low CO2 causes warming, which is why this is a controversial paper. These are all of the cycles we get. So and somehow from this, you've got to deduce why we get interglacials. So ice is this gray color. So ice gets bigger and bigger and bigger until we get an interglacial, and then it drops off. Temperature is red. So obviously as ice goes down, temperature goes up. And then dust is in the purple. And note that every interglacial is preceded by 10,000 years of dust. Big clue, that one. And yet most of the papers I read don't include dust as a feedback agent. And if anyone was doing albedo, the majority of people were doing atmospheric albedo, not surface albedo. Whereas mine is most definitely surface albedo. So let's look at the cycles then. This is temperature versus CO2. So CO2 on the right is in the blue, and temperature on the left is in the red. Today's date on the right, going back 800,000 years. And the temperature comes from ice cores. Now, that's a bit of a problem because you can only do this in the south. So these are Antarctic ice cores. Because in the north, we've only got 130,000 years of record. In Greenland, there's no more than that. So if you want a long record like this record, and one of my reviewers didn't understand why I was going to Antarctica, you can only get this information from Antarctica, because the Antarctic I think the most they've gone back to now is 1 million years of ice in Antarctica. Because the ice flows away, of course. It's like treacle, but very, very thick treacle, and it gently flows away into the oceans, either side, sort of thing. And you can see a correlation between temperature and CO2.
Mm.
And this is, of course, one reason why they say that, temperature is modulated by CO2 because there is a correlation between the two of them. Yeah, but when we get an interglacial, temperatures rise before CO2 rises. Now, that's a problem. How can CO2 be feeding back a temperature rise when it hasn't risen? And it doesn't rise for another 700 years. That's a problem. And the reason why CO2 follows temperature is because of oceanic respiration, you might call it. So when oceans get cold, so they're getting colder, they absorb more CO2. When oceans suddenly get warm, they exhale CO2. And so there's bound to be a correlation between the two. It doesn't necessarily mean there is causation. It doesn't mean that CO2 is actually forcing temperature. They are probably not. This is the first cycle we're going to look at. This is mostly precession. This is the Milankovitch cycle. So this is the cycle that Mr. Milankovitch was discovering back in the 1920s. And it's caused by a combination of 3 orbital effects. So it's caused by precession. Again, we looked at this in the pyramid talk. A precession is the wobble of the Earth. Obliquity, which is the leaning angle of the Earth on its axis. And eccentricity, which is how circular the orbit is around the sun. So if you get all of those, and there's also another type of precession as well, which I can't remember for the minute, but anyway, I'll remember soon. If you mix all of those orbital cycles together, you get this blue line. And this blue line is actually recorded here as insolation at 65 degrees north. So the power of the sun, the sunlight, how much heat you're getting at 65 degrees north. And it changes quite considerably. This is in watts per square meter. It goes from, where's the lowest? This is the lowest at 440 watts per square meter, all the way up to 540. So an increase in 20% in the amount of sunlight hitting the northern latitudes. You can see perhaps why this is a northern Arctic phenomena, because the tropics are not changing in this fashion. The tropics get very little change if you draw these graphs for the tropics. This only really happens in the north and in the south. So it should be said, and I should have put on the top here, but this is northern hemisphere. If you did the same graph for the southern hemisphere, this peak would be a trough, and this trough would be a peak. This is why I call this the Great Summer. So here we see it's warm. You can see the red is the temperature, obviously. When we get high insolation in the northern hemisphere, we get high temperatures. But these temperatures are world temperatures, not northern hemisphere temperatures. So warming is caused by northern hemisphere insolation, not by southern hemisphere insolation. And when it's warm in the north, it'll be cold in the south. This is why I call this a great year, a great summer, because it acts like a normal summer. You know, in a normal summer, if it's warm in the north, down in the southern hemisphere, it'll be cold. It'll be their winter. Well, the great year does the same. When it's warm in the northern hemisphere, it's cold in the southern hemisphere.
Mhm.
So it acts like an annual year, but it's a long year. It's 23,000 years long, not 26,000. Remember in the last talk,
Yeah.
we were saying it's 26,000 years because of apsidal precession. That was the other one I was trying to think of. Because of apsidal precession, it's reduced by about 3,000 or 4,000 years. So it's only about 22,000 or 23,000 years long for the seasonal great year. And that's why all of these peaks are about 22,000 years apart, very
I
regular
see.
22,000 years going back into the past. So yes, it's worth noting that this is a Northern Hemisphere event
Mhm.
process. But of course, if CO2 was the feedback agent, there's no good reason why it would be Northern Hemisphere.
Yes.
CO2 is a global gas. It could happen in a great summer in the Southern Hemisphere, which would be here in this trough. Because
Mm.
remember, when it's cold in the Northern Hemisphere, it'll be warm in the South. It doesn't. It only happens in the Northern Hemisphere. Why is that? It's because all of the continents are in the Northern Hemisphere. So all of the continents, and remember, the continents respond to insolation, sunlight, much more than the oceans do, much quicker than the oceans do. And therefore, all of the ice sheets are in the Northern Hemisphere. Antarctica will expand a little bit, but it can't expand very much because it's surrounded by oceans, and the oceans will just melt the ice away. Whereas in the north, when we get an ice age, the ice sheets can spread out way across all of the continents, all across North America, all across Asia, covered in ice completely. And so this is a Northern Hemisphere phenomena because all of the ice sheets are in the north, and therefore all of the albedo responses, the reflectivity of the white ice, they're all in the Northern Hemisphere. And that's why temperature tracks the Northern Hemisphere Milankovitch cycle. So as you can see, we get a peak in the Milankovitch cycle, we get warming. Another peak here, we get warming. And so you can see that this Milankovitch great summer warming is causing temperature change. However, there is a problem because not all maxima cause warming. So these are all the great summers or the Milankovitch maximum, which do not cause any warming. So look at this one, for instance. This is a great deal of warming. It goes up to 540 watts per square meter and no warming at all.
Mm.
Here, again, we get a little tiny bit of warming. Here, we get no warming at all. And likewise here, no warming at all. So we have to explain why this great summer, the Milankovitch cycle, is only intermittent. Why would a solar cycle, I shouldn't say solar, an orbital cycle, why would it be intermittent?
Mm.
There must be a surface feedback that is affecting it. This is not simply about orbital cycles. There must be a feedback agent that is assisting the orbital cycles. So we've got to find out why we have missing ones here. And the obvious reason why we have missing ones is because we've got lots of ice. Bright white ice all over the Northern Hemisphere will reflect all of that extra. So we've got lots of extra insolation here, lots of extra sunlight, 530 watts per square meter. But bright white ice can reflect away 90% of that. And so you're getting none of that extra at all. And so you get no temperature response. That was my theory anyway. It's been mentioned in papers, of course, but some of their explanations for these missing orbital cycles, I think, are a bit odd sometimes, they say. Some people say that the cycle that controls ice ages is obliquity. Remember, this one is mainly precession. The big one in this is precession and obliquity together. But the main one, the chief forcing agent here is precession of the equinox. Here is obliquity on its own with no precession. And so this is the standard obliquity cycle in blue. This time we're going from 0 back to 400,000 years, so not quite as long in this chart. Red is temperature again. The blue is the obliquity cycle, and it's a 40,000 year cycle as we saw before. So about twice as long as the precessional cycle. And again, you'll see that some of the temperature increases are coincident with high obliquity. So here, sort of, here.
Mm-hmm.
And so some people saying it's obliquity. If you look at Hubers, I think his name is, he's written several papers on obliquity being the main reason why we get interglacials. However, we have the same problem because this is the same graph. There are a number of obliquity cycles that give no change in temperature. So here we've got a obliquity maximum and no change in temperature. By obliquity maximum, I mean that's the maximum leaning angle of the Earth when it goes to 24.3 degrees, I think it is. It changes by about, gosh, I can't
3
remember.
degrees? Is it 21
degrees,
or something?
yeah.
Is it 21 and a
Yeah,
half?
it's about,
Something like that.
yeah, there's about 3 degrees. And so sometimes we get no temperature response, like here and here. So even if you want to have obliquity as being the primary orbital forcing agent, you still need to explain why we have these missing maxima with no temperature response. The answer, as we've hinted before, is dust. And this is a dust storm. Dust storms can travel a long, long way. We know where this dust came from because it's been isotopically analyzed and linked to the Gobi Desert.
Where's that photo?
This
what
is
city
just,
is that?
this is I think
stock
this is
image, is it?
America. It's just I mean, this happens frequently in desert conditions. You'll get this throughout the Arabias. They have this quite often. And I think this one's America.
That's fascinating.
And you get these dust storms rolling in. Now, we know this dust came from the Gobi Plateau because isotopically they've analyzed it and shown it comes from there. But also we have the lowest plateau. So the lowest plateau is in central, more eastern China, and it's an area of land that's been covered by this dust. And it has the same record within that because it's meters deep, I mean tens of meters deep, all of these dust layers. And they have 1 million years of dust within the lowest plateau. And so you can see the same ice age record in the amount of dust that's fallen on the lowest plateau. And it mimics and it backs up what we find from the ice cores when we look at Antarctica and so on. You can see the difference in the amount of dust that's been generated. And that dust can get onto the northern ice sheets. It still does. This is the Arctic. And of course, nowadays, what we're getting is a lot of Chinese industrial dust. So this could be affecting our modern climate, that we are getting darkening of the ice age, of the ice sheets from Chinese industrial dust, because they don't really give much of a damn about how much emissions they emit. So this is the Arctic. This is the Arctic as well. And it's not
really
quite,
wow. Yeah,
it's not the bright white, pristine environment you might expect sometimes.
Yeah, fascinating.
And this makes a big difference, of course, to the amount of absorption in sunlight. So this is quite a few people have done these experiments on soot on snow, trying to see how what sort of difference it makes when you get contaminants on snow. So this one is.
You might be able to zoom at the top there.
Yeah, I have to
That's
make it
you.
a little bit smaller. There we go.
Super. That's it.
So on the left, we've got albedo. Albedo is the reflectivity of the ice. One is 100% reflective. 0.2 is like only 20% reflective. So this is dirty down the bottom, white up the top. And this is the amount of concentration of carbon. They were using carbon dust that has been put onto the ice. And you can see how much the carbon changes the reflectivity of the ice. So bright white, old ice, so not fresh snow. Fresh snow is up here at 0.9, 0.95 if you've got fresh snow. This is ordinary ice, and we get about sort of between 0.7 and 0.8 in the albedo. And then the more dust you put on it, in this case, carbon dust, the darker it gets, and it gets darker and darker all the way down here to 0.4. So that's a big change from, say, 0.8 down to 0.4. That's only half the
Reflective.
albedo. Yeah.
Yeah.
So that makes a big difference in the amount of
Light
insolation
absorb.
that you will absorb, the amount of sunlight you can absorb. And because now let's look at this one first. This is a graph, again, 0 on the right, going back 800,000 years. We've got dust in the green and temperature, same as we've seen before, in the red. And these are all the interglacials. Obviously, high is warm and low is cold. What we've done on this graph is we've shaded anything above a certain level of dust. And what you see is every time we get high dust, we suddenly get warming. So every interglacial is preceded by high dust. So high dust, and we suddenly get an interglacial. High dust, interglacial. But we only get the dust when we get low temperatures. And that's important. Why do we do that? Well, because low temperatures, as we saw in that first diagram, low temperatures are also associated with low CO2. So temperature and CO2 go down together because of the oceans sucking up all of the CO2. And CO2, as we saw in that first diagram, is the stuff of life. And so if CO2, this is CO2 levels here, if CO2 levels keep decreasing, then the amount of plant life will keep reducing. And if you get down to 160 parts per million, all C3 plants will die at this point here.
Mm-hmm.
And
Can you go?
sorry, yeah.
Can you go back to that previous graph, just Ralph? Yeah. Like when I look at that sort of graph, and you're going back 800,000 years, there's not a single anomaly of that of where you see the dust increase, and then just after you have these temperature increases. Whereas all of the other explanations we've come across, there's all of these obvious anomalies, as you've pointed out. But that really is like extraordinary. Even if there was one of them off, it would leave more room for uh, unknowables and other variables being a major factor. But that's extraordinary. What kind of response do you get? Have you spoke to other climate scientists when you see that kind of graph? Because that's a standout
Yes.
one there to me.
Yeah, well, the money graph is this one. We'll look at this one in a minute. Yeah. But yeah, there is a very high correlation there, very high correlation.
That's extraordinary.
And the question then becomes, is it causal? And of course, some people might argue that it's not causal, that,
Mm-hmm.
it's not really the dust that's actually doing the feedback of orbital cycles. But the correlation is actually very strong. This is a scatter plot of CO2 at the bottom and dust on the side here on the X axis. And you'll see the scatter plot has a very good correlation. There's a high correlation. The straighter the line, the higher the correlation between the two. So it seems likely that dust is the feedback agent. And we don't need CO2 at all in this. If you read Ganopolsky, he's trying to put dust in along with CO2 because you've got to have CO2 because otherwise I don't get my grant. It's not necessary. And he's got the wrong reason why there's dust there in the first place. He needs the ice sheets to move across the ground to disturb the ground to get the dust. But that's not necessary because that's not how ice sheets work in the first place. Ice sheets spread and then build. They don't build and spread out like some Disney film.
Yeah.
So yes, we will see that this dust, most of it came from here. So this is the Gobi and sort of northern China regions. And at present, most of this is steppe grassland. I mean, we call it the Gobi Desert, but most of this is steppe grassland. So it grows grass. Not good for anything else. You can't use it for arable agriculture, but you can use it for pastoral. And of course, you get all the nomads with their sheep and their horses and whatever. And that's the Gobi Desert. So the Gobi Desert is not producing dust really at present. The only one is the Taklaman, which is over here somewhere in the lee of the Himalaya, which is a permanent shifting sand desert even today. This is a image of rainfall across the Gobi, and of course, blue is relatively high rainfall. The yellow is less. But they're still saying down here, I think, 42 millimeters. Well, 42 millimeters, well, you can still grow things with 42 millimeters of rain. So it's not a pure desert. But you're talking about correlations. This is the money graph. And here, again, at the bottom, we have dates. So today's date going back 800,000 years. On the left, we have CO2, and CO2 is in the blue. And on the right, we have inverted dust. Remember, inverted. And it's logarithmic as well. So a little change in CO2 means a huge change in the amount of dust. And the dust is in green. And there is a perfect correlation between the two. Just as we saw with temperature and CO2 in that first graph, there is also a perfect correlation between dust and CO2. And this time, I think it's causal. So the lower the CO2, let's do this the other way around. So the higher the CO2 is the blue, the less dust, because dust is less going upwards on this graph. So high CO2, less dust. Low CO2, loads and loads and loads of dust. And it's proportional all the way down. And one of my reviewers couldn't understand why this would be proportional. It's because we have mountains, we have upland areas. So if the Earth was all flat, then you would not get this correlation in this fashion. But because we have upland areas, the upland areas will start losing their CO2 before the sea level areas. Again, one of my reviewers had no understanding of how this happened. He said, I think we mentioned this before, that there's the same concentration, the same percentage of CO2 at altitude as there is at sea level. And so you will not get effects of plants dying off first at high altitude. And I sort of looked at this as an explanation. So I wrote back and said, well, why do we have emergency oxygen in aircraft? We have the same percentage of oxygen at altitude, up at 35,000 foot, as we do on the surface. So why do you have emergency oxygen? Because the partial pressure is reduced.
Yeah, I see.
And therefore you're going to be starved of oxygen and you're going to die. Well, same happens to plants. At higher altitude, if there is less, there will always be a lower partial pressure of CO2 at altitude, obviously, to the sea level. But as CO2 concentrations reduce, you will get to a point where at, say, 2,000 foot, you get to that magic 160 parts per million where plants cannot live. They'll still be living at sea level because they will have a higher, and we'll look at the graph in the table in a minute. They will have more CO2 in terms of partial pressure at sea level. And so they will continue to live. But at higher altitude, they're getting starved. And that's why it's the Gobi that is important, because a lot of this is high ground. Well, not super high ground, 2,000 foot, but that's enough to make a difference between whether you're going to live or whether you're going to die as a plant. And that's why we get this correlation as CO2 reduces, because this effect only happens at high altitude to start with. And then it gets lower and lower and lower. This effect will come down the mountain side. And we didn't actually include it in the paper, but I thought it was a very good graph, actually. We did a correlation of the amount of land area. We got it from a satellite record, and it was a nice record. It gave you the amount of land area at any particular altitude, say from 5,000 foot, 4,000 foot, 3,000 foot, and the amount of land area that you could find around the world at each particular altitude. And of course, the amount of land area increases exponentially the further you come down, because there's more lowlands than there are highlands. And it matched perfectly with this CO2 and dust graph. And that's why you get this correlation between CO2 and dust, because it's coming down the mountain side, as it were. Initially, at 5,000 foot, there's not many areas that you're going to impact. But when you come down to 2,000 foot, there's a lot of areas you're going to impact and kill off all of the plants. And so we get CO2 deserts, which is a term that that they did not like. We're all familiar with precipitation deserts, aridity deserts. No water, no plants, you get a desert. Well, these are CO2 deserts. No CO2, no plants, you get a CO2 desert. Yeah, this is, we were talking earlier about how close we came to all life on Earth dying. We came down to 2,000 foot.
Wow.
At 2,000 foot, all plants at 2,000 foot and above had died.
That's crazy.
Forming these great CO2 deserts, and that's where the dust came from. It came from these enormous CO2. That's where the lowest plateau came from. It was all the dust coming off the Gobi and flowing down into eastern China and forming the lowest plateau. And then, of course, that it settles on the northern ice sheets. Remember, all of North America was covered by the Laurentide ice sheet. And then we get the European ice sheets and Greenland and so on. The dust settles all across those. And we know it settled across them because we can see the dust in the record, in the ice cores. And this is just a quick comparison over what we might expect, depending on the amount of dust. So fresh snow, we get, if we had 0.85 albedo, we saw the albedo chart before. If the ice in the Laurentide ice sheet was 0.85 albedo, we would get the 65 watts per square meter would be reflected back. No.
No, it absorbs more. Yeah.
The other way around. 65 watts per square meter would be absorbed. into the ice, and therefore
It's
you're
the
not
energy from the sun.
energy from the sun. So
Yeah.
you're not getting much warming. But if you have 200 parts per million dust, that goes up to 135 watts per square meter. If you get 400 parts per million dust, which is quite possible from the amount of dust we were getting, you would get 180 watts per square meter. So we're trebling the amount of sunlight you're absorbing on the ice. And that's a huge increase. And I was criticized again because I was not globalizing the amount of warming. So if you're doing this with CO2, they have 4 watts per square meter as being the extra you will get with a doubling of CO2. So if you're going from 200 parts per million to 400 parts per million, that will give you an extra 4 watts per square meter. We're talking here 140 watts per square meter. And they were complaining that I was not globalizing this data. Oh, you've got to spread it all over the world. No. What melts the ice, the snow and ice in Canada when you get to a northern spring? It's not the temperature in Argentina. It's the sunlight and the warming in Canada itself.
Exactly.
So this is a regional effect, not a global effect. And we know it's a regional effect because, as we saw before, interglacials are only a northern hemisphere event. They only happen on northern hemisphere great summers. Therefore, it must be regional. It cannot be global. Therefore, there's no point globalizing these figures here and spreading them out all over the world. They are what they are. At 65 degrees north, during a great summer, we can have 140 watts per square meter extra absorption. Not 4 watts per square meter that we get from CO2. You can see why I think CO2 is a minor player in this. We get 140 watts per square meter. Now that is something that can melt an ice sheet in 5,000 years, because the ice sheets will melt in 5,000-6,000 years. It's a very quick process. And this is the ice. This is the dust. So it's still there. This is from Greenland, and as we said before, the ice is like molasses. It's like treacle, and it slowly spreads itself out across Greenland. And this is where it's reached the coastline. Obviously, you can see it's on the coast, and some of that dust is still there. And here is that dust from just before the Holocene interglacial, our recent interglacial. Why do we get this shape? Well, we saw in the first graph, we saw the Younger Dryas. So we had sudden warming. Sudden warming is no dust, of course, because as soon as you get warming, you get more CO2, and therefore the plants recover. Therefore, the goby gets covered in grass, and therefore it's not producing any dust anymore. So as soon as you get warming, the dust goes away. And then we were plunged back into the Younger Dryas when it was cold again for 1,000 years, and the dust came back again. And then it warmed again into the Holocene, and all the dust goes away. And that's exactly what we see here. So going back to that same picture. So here's all the dust. So I've flipped that upper graph around so it matches what we see here. So this is the glacial maximum when it was coldest. This is the glacial maximum when it was coldest, and we see it's covered in dust. Then we had this break in the dust, so the dust went away. The dust went away because it suddenly got warmer. So that was the initial warming. Then the dust came back again because of the Younger Dryas cold period. And that is the Younger Dryas there. That little band of dust when the dust came back again.
So interesting that.
Yeah, because we were plunged back into the Younger Dryas.
Mm.
And then the dust goes away again, of course, because then we warmed into the Holocene maximum.
Mm-hmm. Yeah, no, it's wonderful how it leaves its its imprint in nature for us to look at later dates here. Like that's so cool. You can look at that and put that together with it.
Yeah, it's there in the record. You can see it. It's
Yeah.
there. And then why do we get this in Greenland? Again, one of the reviewers asked this question: Why do you only get this in Greenland and not the Laurentide ice sheet? Because the Laurentide ice sheet, of course, is all gone. Well, we've only got the Greenland ice sheet because it's stuck in a bowl. So this is the land area of Greenland. This is not the ice. There's no ice. They've taken the ice off. This is done by radar survey, obviously. And these are the mountains that form Greenland. But Greenland has been crushed by so much ice for so long that it's actually formed a bowl. This is actually below sea level down here. So it's actually, yeah, it's a bowl and it's below sea level. So the ice cannot flow off Greenland. It's stuck. Remember I said that ice is treacle? Well,
Yes.
the treacle is stuck because it's got a ridge of mountains all around the outside. And so the sea cannot touch the ice. It cannot melt the ice. So it can only melt very gradually because it melts at the base because it's so, there's so much pressure from 3 miles of ice above it that it actually warms up down the bottom and it can actually melt because of the high pressure. So that's why we still have a Greenland ice sheet. Now, this has knock-on effects because I think a lot of climate science is incorrect. And this was my biggest change to standard climate science. This is a PMIP map, which is a map of the past, obviously, in climate. And this is precipitation. So this is precipitation at the last glacial maximum. This is like 20,000 years ago. And this is precipitation. So high precipitation is blue. This is the world, of course. You can see Americas, Africa.
Yeah.
High precipitation is blue. Normal is white. And lower than normal is these oranges and going down to reds. And this is what they think was happening 20,000 years ago, 50,000 years ago during the Ice Age. And what they've ended up with is this band, this little thin band of no rain in the tropics. And I'm looking at this thinking, nah, that don't look right. We've got no rain up here, of course, because, this is the Laurentide ice sheet. This is really, really cold up here. Cold air is normally dry air. And so you get no rain on these ice sheets. But here in the tropics, where it's nice, remember, it's still warm in the tropics. Temperatures drop 12 degrees over North America. In the tropics, they only dropped 2 degrees. So it's still warm. It's still balmy. There's plenty of water there.
Yeah.
You're going to produce rain, aren't you? So why do we get this band of no rain right through the tropics, right on the equator? Well, it's because how they calculate temperature in the past. And they've got it wrong.
Mm.
This is a basic error in climate science. They've got this wrong. So one of the ways they get temperature is through looking at silt deposits in the ocean. So you get all of these Foramas, I forget anyway, little tiny animals you get. And depending on the species you find is very highly correlated with the temperature. So you can drill through the muds in the bottom of the ocean and you can have a look at all the different microbial animals that are living there. And you can see what the temperature of the oceans were. So you can gauge how warm it was. But for the atmosphere, they tend to do it on tree lines. So here is a typical tree line. And above that particular line, of course, there are no trees, and trees are dependent on temperature. And they generally say it's something like a 10-degree soil temperature in the summer. If you don't reach 10 degrees in the summer, you won't get any trees. And so that's why you get this tree line. And from these tree lines, you can assess what the temperature was back in the past, because many of these tree lines are visible. Ancient tree lines are visible on the hillsides. And so you can see how cold it was or how warm it was in the past. And that's where they get these precipitation maps from as well. However, what they haven't realized is that tree lines are also modulated by CO2.
Yeah, by the partial pressure. Yes.
Yeah, by the partial pressure of CO2, because CO2 is not causal in the current climate. And so they probably didn't think about this because we've got plenty of CO2 at present. And so CO2 has no effect on tree lines. However, during the Ice Age, we had much less CO2, and therefore CO2 became the dominant factor that was changing and modulating tree lines. So here's a quick table, which I drew up based on all of the available data from, I'm just using the standard 6 degree per 1,000 meters lapse rate in temperature. So as you go up 1,000 meters, the temperature reduces by 6 degrees. Now, the problem with this tree line here, when they did it on temperature, is they were ending up with huge, great lapse rates. So we normally go for 6 degrees, 2 degrees per 1,000 foot is what we do it in imperial. But they've gone metric, so 6 degrees per 1,000 meters. They were ending up with 8 degrees, 9 degrees per 1,000 meters, which is impossible. Absurd lapse rate. And the bigger the lapse rate, the drier the air. Because the dry lapse rate is much higher than the saturated lapse rate. That's just standard atmospheric science. So if you've got a very high lapse rate, you've got very, very dry air, and therefore no rain. And that is why you end up with this red swathe across the tropics, is because they've miscalculated the tree line data. So if we look at my data, so let's have a look at tropical tree lines. So interglacial temperatures I've got on the top. So here, this is surface, 1,000 meters, 1,500 meters, 2,000 meters, 4,000 meters going up the mountainside. These are the temperatures, standard temperatures you'll get in the tropics. 28 degrees surface temperature, roughly, average. And that's the temperature decreasing as you go up the mountainside. This is the partial pressure of CO2 from the industrial level, pre-industrial level of CO2, which is about 300 parts per million, going up the mountainside in terms of partial pressure. So these are partial, these are parts per million equivalents.
Yes.
In terms of partial pressure. So not the actual parts per million, but the equivalent partial pressures, going all the way up down to 180 parts per million equivalent. So that's interglacial. That's the current climate that we have at present. Now, glacial is this line. So glacial temperature, I've put it 4 degrees cooler in the tropics. That's probably excessive. It probably wasn't that bad. So 24 degrees instead of 28. And then this is the reduction in temperature using the standard 6 degrees per 1,000 meters, all the way down to freezing point at 4,000 meters. And then we get the CO2 parts per million equivalent.
Yeah. Yeah.
And now this is the glacial one. So we went down from 300 parts per million down to 190 parts per million at the surface. That's pretty much what we got down to at the surface. But of course, at altitude, we have much less because the partial pressure reduces. So the equivalent parts per million goes down to 170, 160, 150, 115. Now, the problem is 160 parts per million is the point at which all life on Earth will die, all C3 plants, rather. And remember, all trees, pretty much every single tree, is a C3 plant. There are very, very few C4 plants, trees. So C4 plants cannot live at cold temperatures. They tend to be tropical, like, sugar canes and maize and so on. They like warmer temperatures. If you're going up a mountainside, you'll find everything on a mountainside pretty much is all C3 plants. And these are the ones that die off first from a lack of CO2. And so once we reach 160 parts per million, C3 plants cannot complete a life cycle. And so at 1,500 meters now, during the glacial period, it is CO2 that is the limiting factor.
Mm-hmm.
So in terms of temperature, the limiting factor is about, I've got 16 degrees and 4 degrees there. So about here, about 3,000 meters, that is the limiting factor in the current climate. In the glacial era, the limiting factor is CO2 at 1,500 meters. So much lower down the mountainside. All of the trees were dying off because of CO2. Therefore, we don't need to have these absurd lapse rates that they got on their calculations. We don't need to have this absurd dryness that they had. We can have normal lapse rates and normal precipitation because it wasn't the temperature. The temperatures were not going down that much. Their data is incorrect because they were using tree lines modulated by temperature instead of CO2.
I see.
And so it's quite possible that tropical rainfall was the same during the Ice Age as it is now.
Mm.
There is no reason to suspect that we had these arid conditions across the tropics. And likewise for the Gobi, because they were saying that the Gobi had to be much drier. But the Chinese are saying no, they have no record, looking at the past records of the Gobi Desert, they have no records saying that the Gobi was drier. If anything, the eastern Gobi was actually wetter than it is now. So the Gobi did not become a desert because of a lack of rainfall. It became a desert because of a lack of CO2. And so that's a big change to these PMIT maps. These maps are used in all of climate science. And so this is one of the basic foundations of climate, and I think it is incorrect.
I see.
So yeah, that's my modulation of Ice Ages paper.
Yeah.
Fairly influential, I think, with all of the downloads we've had from it.
No
What
doubt.
else have I got down the bottom here? Nothing really of interest. This is just a cross-section through Antarctica. This is all ice, and you can see the ice is in layers. And I just like this picture because it shows that the ice flows like a liquid, like a very thick molasses, and it's flowing from right to left here. And where it hits a mountain, it forms eddies and waves, exactly like the atmosphere would. When the atmosphere goes over a mountain, it forms these wave clouds. Well, the ice is forming wave clouds in exactly the same fashion. So when you're drilling this ice, you have to drill it in the right place. You can't drill it where there's all this turbulence down the bottom. You have to find somewhere that's relatively smooth, like here, where you'll get a nice cross section through the ice without any of this turbulence going on down the bottom.
Hmm.
So that is my Ice Age paper.
Yeah, super. Yeah, no, it's fascinating. And maybe we'll chat a little bit about the reception it got when you initially put it out, or yeah, what other receptions you've had? I appreciate there was a lot of pushback then from the climate scientists of the mainstream. Is there any other notable sort of receptions you got, or did you find many people agreed with it, or find it sort of enlightening? Because it's when you go through it, it makes perfect sense, you know. And it's strange that they don't calculate the albedo in a lot of these models. Which is wild. Yeah,
Yeah, that's one of the big
yeah,
differences. I think
mm,
in general, people have tried to ignore it because it upsets the apple cart. It's saying the opposite of the standard climate dogma that everything is modulated and controlled by CO2. Um, and so this is saying that CO2 is only a minor player, and there are only a handful of climate science that are actually saying that. There are a handful of climate science that are quite happy to say that CO2 only gives, well, at present, it only gives about 1 degree for a doubling of CO2. Obviously, when CO2 was only just starting, between 10 parts per million and 100 parts per million, it was quite effective then. But when we come up to 300 parts per million, going up to 400, it's only about 1 degree for a doubling of CO2. So it's not that powerful an agent. And my paper underlines that. It's saying that the primary um, control of temperature is actually albedo. And that may be happening at present because we have this darkening of the ice up in the Arctic because of industrial dust on the Arctic. Another chap called Paul Burgess has done what I think is a good paper that very accurately tracks our present temperatures. So all of the models they make from all of these different agencies, there's something like there's something like 200 different models they've made of world temperatures and so on, predicting the future, and they are all running too hot because they've exaggerated the effects of CO2. They have CO2 up at 3.5 degrees for a doubling of CO2. Paul Burgess has got his down again at 1 degree for a doubling, but mostly controlled by this time cloud albedo. So this is in the current environment, not the ice ages, but in the current
mm,
environment. Clouds have an equivalent effect because, of course, if you get lots of clouds, they reflect the insolation, the sunlight away.
mm-hmm,
Clouds also can hold heat underneath them as well, so they have a dual effect. But the primary effect is they actually radiate away insolation, so you don't get the sunlight in the first place.
mm,
And so he's done a model that mostly includes clouds and oceanic cycles, and he can modulate the temperatures exactly over the last 100 years.
mm,
So the primary modulation agent is actually, according to his paper, it's albedo, albedo, with a slight rise that is caused by CO2.
mm-hmm,
But the CO2 is only an underlying rise. It's not controlling the temperatures that we have decade to decade. That's all
mm.
controlled um, by albedo of the atmosphere, the clouds. So it's entirely possible that all of these scare stories about CO2 in the current environment are all wrong.
Yeah.
And that's why
Mhm.
temperature is not following CO2 in the fashion that they have in their models.
Yeah. Yeah. And it's not possible really to extrapolate his work further back than the last 100 years. You know, when we're talking about these millions of years or hundreds of thousands, your graphs are going back to 800,000 years ago. Um, are you able to put sort of a percentage on how much you think the dust albedo of the effect of the on the ice sheets contributes then to this overall change in temperature? Do you think it's like responsible for 90% of it, and then this cloud stuff is less, and the oceanic sort of changes is less? Or
Well,
I know it's probably a difficult, yeah.
in the current environment, of course, we reach a maximum. That is another problem that this explains. So if we go back to screen share just very quickly and share that, if I go back to one of the original graphs, um, so in this graph, we can see that as temperature increases, so does CO2 increase. And so as CO2 is increasing, it's forcing the temperatures to increase, and that will increase the amount of CO2. So we end up with this runaway greenhouse effect where it just keeps on rocketing away. And we get what scientists have been warning about for ages. We get a runaway greenhouse effect.
Yes, this is this end of the world type stuff. We
End
must
of the
stop.
world, yes.
Yeah,
Yes.
or else. Yeah.
The world is going to end in 7 years. Isn't that what
Was it Al Gore, Greta Thunberg, one of these?
that was the Greta the Gremlin, I think, said that one. 7 years we had. That was like 10 years ago.
How dare you? How
How
dare you
dare
kill
you?
our planet? Yeah.
But of course, it doesn't run away. What we get is they all end at the same temperature. So
Yes.
we got
Yes.
1, 2, 3, 4, 5 interglacials here, all ending on about the same temperature. So why do they end at this point? Well, if we throw CO2 out of this picture and we replace it by ice sheet albedo, at this point, we run out of ice.
Yes.
All of the ice has gone. All of the ice sheets have gone. The Laurentide ice sheet, the European ice sheet, they've all gone. And so there's no more changes to the albedo. So we run out of puff, as it were. All of the interglacials have to stop at that point because there's no more change in the albedo because there's no more ice to melt. It's all gone.
And you think it's mainly albedo then? Where would you rank the other greenhouse gases that they sort of fearmonger over? So with methane and these kind of things, and how
Well,
does that all
methane
play in?
is the smallest of the three. I mean, it's the most
Mm,
powerful, but it's the smallest of the three. I think CO2 is sitting at 1 degree for a doubling of CO2. So if we're going from the bottom here 180 up to 300, that's only a doubling at best. So we're talking about only at best a 1 degree change due to CO2. And yet what we see on the left-hand side here is a 10, 12 degree change. So that's not all being caused by CO2, that's being caused by something else. And it's not all due to orbital cycles, as we've seen, because orbital cycles do not explain the warming, because half of the orbital cycles don't produce any warming at all. So clearly it has to be due to albedo, the bright white ice reflecting it away. So CO2 at 1 degree for an ice age as for an interglacial, instead of the total 12 degrees. We're talking about CO2 only being 10% of the effect. So it's a very small player in the interglacial modulation system. And likewise with modern temperature, at 1 degree temperature rise for a doubling of CO2 is not actually going to be a problem, because we're at 400 parts per million. We would have to get to 800 parts per million before we would get just 1 degree extra warming,
yeah.
which
Yeah.
is not a great deal.
Yeah.
Nothing really to worry about.
Yeah.
And as far
And
as the next ice age is concerned, we're currently in a low eccentricity. I don't have the graph where it goes into the next millennia, but we're in low eccentricity at present. So we're going to be in a very mild great winter. So ice ages are forced by a very deep great winter, which lowers the temperatures in the northern hemisphere by an enormous amount, as we've seen from those graphs when the amount of insolation reduces by, what was it, 100 watts per square meter or something. That's a huge amount of cooling. But we're in a very mild great winter this time, and we're almost at the base of it already. So there's not going to be very much more cooling to come. So I don't think, and the maximum cooling is in about 1,000 years, something like that. I don't think we're going to get an ice age off this one anyway, because there's insufficient cooling because it's a very mild great winter. And so there won't be another ice age. And if there is another ice age, if the ice sheets do start to spread a little, well, we know how to counter it. We just spread the ice sheets with carbon dust, and that will send the ice sheets away straight away. So it won't take very much modification to prevent a new ice age. So I don't think the new looming ice age is much of a problem. And we've got a mild climate for the next 50,000 years. So it's fairly stable for the next 50,000 years because eccentricity is low.
Mm.
So yes, we're not going to get another ice age.
And I was going to ask you a bit about the end of this Younger Dryas period, and maybe these impacts or different anomalies that has impacted these ice ages. However, maybe this is setting us up for the next talk. Do you want to give us a little bit of information what we might be chatting about next? You'd mentioned something earlier at the beginning.
Yes. So this ice age cycle brings us on to why we have a Younger Dryas, which is that cold period that we saw.
So we'll go into
previously.
depth of this on the next episode. But yeah, we're coming up to 2 hours.
Have we got time to do that now, or shall we leave that till next time?
Would you be okay if we do it the next time, Ralph? Would that be all right?
Yeah, we can do that next time.
I'll come with a few more.
Yeah. For the next episode, then we're going to be looking at the Younger Dryas. And as a quick recap, this is the Younger Dryas. Today's date here on the right, going back 50,000 years. We'll talk about this in the next talk while we've got this up and down. The red is Arctic temperature. The blue is Antarctic temperature. And we had this temperature rise, and then suddenly we went back into the Younger Dryas. And I think there was another reason for that. So the climate is affected by many, many things. You know, it's a very complex system. And I think there was an external problem that impacted the Earth at that point, and that's why we had the Younger Dryas. The other explanations I don't think stack up why we had this sudden cooling event when we should have gone straight up into a interglacial, and it should have been warm all the way across the top here. But we had 1,000 years of cooling. So we'll look at that in the next talk as to why we should have had that cooling, because it's an interesting problem that most people have never heard of, even though the effects of it are all over North America. Everywhere you go, especially on the east coast of America, you find evidence of what happened during the Younger Dryas. And yet it's still highly contentious. Like a lot of these problems, the science is not settled by any means. And so we'll look at why we had this sudden cold period for 1,000 years, which affected pretty much most of the world. Not so much in the south. You can see from this diagram, the blue line is Antarctica, and you can only see a small drop in temperatures in Antarctica. But it was still recorded in Antarctica, so they still had cooler conditions even down in Antarctica, but they only changed by a couple of degrees, whereas the northern hemisphere, the Arctic, went down. Well, what have they got here? We went down from almost 0 to -15, so it was a 15-degree
Yeah, it's
drop in temperature.
extraordinary.
Yeah,
Yeah,
it was
in a
very
short period of
sudden.
time. Yeah,
Yeah,
yeah, yeah.
very, very sudden and very, um, very strong cooling, if you
Hmm.
can put it in those terms.
And maybe just to set up one more wee thing, this wouldn't happen to coincide with a big flood around the world, would it, Ralph? Or or should we
Well,
leave this for the next chat?
there were floods, of course, because when we had that warming, we also had. I'll just go back into screen share.
The reason I'm bringing it up is um, the start of civilization. We sort of find these things around the end of this period of the Younger Dryas. And then maybe this is where some of these ancient myths of this great flood that happened, which is recorded in all these different civilizational records and mythologies, more accurately. And so I was wondering,
Yes. Well, we had a great rise in sea levels. So you see here, it's probably best to see it from the Antarctic record here.
yeah,
So we went from what's that, -8 degrees up to 0 degrees. These are temperatures down in Antarctica. Now, as we warmed, that's over just over 5,000 years, call it 6,000 years, something.
mm,
Sea levels rose by 140 meters.
that's unbelievable.
Yeah, that's a big rise in sea levels. So, I mean, there was no English Channel. Um, England was connected to Europe. Ireland was connected pretty much to England. It was all one great landmass because the sea levels were 140 meters lower than they were. All of the North Sea was inhabited by people. There were not towns because we're talking about a long time ago, but there were a lot of people living in the North Sea
Mm,
because it was dry land. It was very productive. It was full of trees at this point here. After the ice sheets had melted away, because the ice sheets didn't quite. I don't think the ice sheets went over the North Sea, but they went down to Yorkshire and they went down to Cheshire. But because the North Sea was lower, I don't think there was many ice sheets down there. But all of that flooded, of course, after the ice age ended. And so people were pushed out of those places. They had to retreat back to the positions we see today. So there were a lot of civilizations that have been left on the coastal plains, and we might find evidence for them if we look closer at the sunken land. Well, not sunken land, but just the continental. What do they call it? The continental sheet upon which the continents sit. Anyway, that area
the
out to the
shelf.
sea before you go into
Yeah.
the ocean. Um, and also we had the Black Sea flood. So the Mediterranean lowered down, of course, because all of the sea levels went down. The Mediterranean might have been cut off a little bit from the Atlantic because obviously the Mediterranean is only joined at the Straits of Gibraltar. I'm not quite sure how deep the Straits of Gibraltar is, but the Mediterranean was largely sort of cut off from the Atlantic. But the main thing that happened was the strait to Constantinople was completely closed. So the Black Sea was cut off from the Mediterranean. So the Black Sea dried up. So sea levels in the Black Sea went down by a huge amount because the Black Sea is actually quite deep. It goes down, I think, about 2,000 meters or something in the center. But anyway, a lot of the Black Sea evaporated away because there's not enough water coming into it from the rivers coming into the Black Sea. So sea levels went down and down and down. So people were living around all of the Black Sea. And then when we came to this point here, which is like 12,000 years ago, and sea levels were rising, finally the sea was able to breach, the Mediterranean Sea was able to breach the gap at Constantinople and push its way through back into the Black Sea. And there was this enormous great waterfall. You can imagine the size of the waterfall. What the Greeks called the clashing rocks of the Bosphorus there, where the gap between Asia and Europe across the Bosphorus, I'm just trying to imagine what it is. It's like 300 meters or something wide, where you see the bridge going across Istanbul or Constantinople. Maybe it's more than that. Maybe it's 500 meters wide. All that water was rushing in down into the Black Sea and rushing in at a huge rate. I think they calculate something like 100 miles an hour or something for this water rushing in.
Jesus. Yeah.
And flowing down into the Black Sea.
Wow.
And the Black Sea was filling up. And I'm guessing here, because it's a long time ago I read about this there was a couple of American scientists wrote a book about this because they did the survey work of the Black Sea, and they were the first people to find that the Black Sea had actually, well, not completely dried up, but a lot of it had dried up. And they wrote this book about it. I think it filled back up again within about 20 years or something.
Right. Yeah.
So if you were living, as many people were, down on the
Yeah.
Black Sea,
Wow.
you would have to start walking quite fast. And I think it was something like 2 kilometers a year or something you would have to be walking to keep away from the flood as it was filling up the Black Sea. So that covered a lot of ancient peoples who were living down in the Black Sea. That was a big major flood that people would have known about, and they would have written about that the land was flooded. The other reason for with the flood myths we have is because the ancients regarded the skies as a sea, the great ocean in the skies above. As above, so below. And so that's why we have Ra used to sail an ark across the heavens above, because the heavens above were a big ocean. So you could sail the seas and you could sail the seas in the cosmos above. And the ark of Ra sailed the seas of Nu, from where we get Noah or Noah. And the ark of Ra held the gods 2 by 2, because all of the gods are male and female. All of the gods were paired up. The main 9 gods were all paired up, male and female. So you get, Thoth. His wife was Maat, male and female, the 2 twin gods, So they were all dressed as animals, of course. So all of the animals were 2 by 2 in the ark of Ra, sailing across the cosmic seas in the heavens above. So that is part of the reason we get the sort of Genesis flood myth. It's a retelling of the original Egyptian creation myth, because the Ark of Ra was sailing across the seas of Nu, which were the seas of chaos, and there was no order in chaos. And then they found the first land of real land of rationality within the chaos of Nu. And that was found by the phoenix, so sending off a bird to find the first primeval land in the chaos of Nu. Well, again, that's very reminiscent of the Genesis story, sending out the birds from the ark to go and find the first pieces of land in the great ocean of the flood. Well, yes, but in Egyptian terms, this was the flooded cosmos above us. And so I think a lot of the Genesis story comes from that Egyptian foundation myth, as to how the world was created. So we have many reasons why people might think there was a flood. And then, of course, you go to places like Giza and you look at Giza and it's full of seashells.
Right. Yeah.
There are
Yeah.
fossilized seashells all over the Giza Plateau because it's a limestone plateau.
Hmm.
And so, you would see standard seashells that you would see on the beach today, plus ammonites and various other things, all sitting in the limestone at Giza. And so, if you're looking at this, on the Giza Plateau, which I don't know, it's like 50 meters above the land down below, you would say there must be a flood. I mean, you go to the top of the Alps and you see seashells all throughout the Alps.
I didn't know that. Really?
Oh
Right.
yeah, yeah.
Yeah. Yeah. Yeah.
Yeah, you
Yeah.
go to the top of the Himalaya. The Himalaya is all limestone, and so you'll find seashells right on the top of the Himalayas. And so a lot of people would have also, from that, said that there must have been a great flood. Otherwise, why have you got seashells all over the Alps?
Mm.
Um, so there are many reasons for this flood myth to have arrived. There was the, tectonic uplift. I mean, but that happens over millions of years, and that's why we get limestone at the top of mountains. We get the real floods that we've actually had, like the Black Sea flood and the Zaklian. Is it Zaklian flood? Um, we're going back millions of years here. Well, not that many, only about 6 million years or something, 10 million years. The whole of the Mediterranean dried out. There was no Mediterranean.
Right.
So the Pillars of Hercules, that entrance to the Atlantic, that was blocked for some reason. Maybe due to tectonic influences, if Africa was pushing up into Europe and just closed off the Straits of Gibraltar. Anyway, it was closed off for some reason. And because there are not enough rivers coming down into the Mediterranean, it started drying out. And it dried out until there was no water left, maybe a little tiny pool at the bottom somewhere. Because again, the Mediterranean is quite deep. You can go down, I think you can go down 2,000 meters. I'm not quite sure. Anyway, it's a long way down. It's quite deep at the deepest parts of the Mediterranean. And so people, millions of years, no, there wouldn't have been people. Anyway, animals, plants, everything would be living down in the bottom of the Mediterranean.
Yeah.
And they know it dried out because they were drilling down through the Mediterranean, through the muds, through all of the cores, and then they broke their drill bit. And so they pulled it up and they did it again and broke it again. And then they got a much stronger drill bit and they drilled it properly. And they found the bottom of the Mediterranean is all salt,
Right. Right.
thick layers of salt. And you only get that, of course, if you dry out the Mediterranean. It becomes one big evaporation basin and you end up with salt pans down the bottom. And they totally dried out into solid salt. So we know the Mediterranean dried out. And then they had the Zaklian, I think, I'm probably mispronouncing that, flood, which was several million years ago, where the Straits of Gibraltar opened, maybe because the sea levels were rising or something. And that had this major flood that came in through the Straits of Gibraltar, which flooded the whole of the Mediterranean. And that was the biggest waterfall in history, I think, probably the largest one ever.
Yeah. That's fascinating.
Because they've had many big floods like this. If you look up at the Northwest American Badlands, I forget what they're called now, but anyway, they've got what they call these scoured lands over in the northwest of America, where the water from the ice sheets that were melting, because remember, these ice sheets melted fairly quickly, 6,000 years, all these great Laurentide ice sheets melted. And occasionally, because it's flowing across the land and the land is bumpy, it's got mountains and hills and whatever, it got stuck. And it got stuck because maybe a finger of ice was pointing down, the mountain valley. And so it blocked the water so it couldn't go. And so it built up a huge, great reservoir. And finally, because ice is lighter than water, so the water can actually get under it and lift the ice, eventually there's enough water in this great big reservoir behind it that it can push its way through that ice dam. And you get this great scouring as this enormous great lake empties across northwestern America and scours the land and forms these enormous great deep trenches which can only be formed by fast-flowing water. And then they have these ripples, like you get on a beach. You go to a beach and you get all these nice little ripples that you walk across. Well, they've got ripples that are 100 meters wide
I see.
as
Yeah.
this water was flowing down a
It's
vast lake.
extraordinary, isn't it?
Ah,
Yeah, yeah.
destroying
Okay.
everything in its past, in its
Unbelievable.
path.
Mm-hmm.
And that happened several times. Because
Mm.
remember, we've had many ice ages, and they say during the last ice age that these pulses happened on numerous occasions,
Mm-hmm.
maybe 10, maybe 20 of these pulses of water. Because as the water flows out, the ice sort of blocks off the valley again. And so the water then builds up once more again as the ice sheets are melting. And then the water is able to force its way through the ice dam and flow off down towards Washington State. Yeah, the land has been greatly affected by these ice sheets and these ice ages.
Yeah. Yeah, well, we'll maybe go into more detail of this again just on the next chapter with it. And absolutely, if anybody has any questions, please leave it down in the comments section below. We'd be happy to go through those. We'll be definitely doing a future episode on them, but maybe try touch on some of them at the next time too. Once again, Ralph, thank you so much for all of your time and for walking us through this paper. This has been really fascinating, and it's a very contemporary topic. You know, it's affecting everything, these sort of energy policies and this climate hysteria and whatnot. So it's great to see a bit of light and a bit of sense on the topic, really, with it. So yeah, thank you very much again, Ralph. I really appreciate your time. Everybody, please find links to Ralph's his work and all his social media sites down in the comment section below. Thank you again for watching, and we'll see you at the next episode. Thank you, and all the
Great to be on
best.
the show. Thank you.
Thank you, Ralph. Cheers.